it says a communication satellite orbits the Earth at an altitude of A miles. So A is a number. So A would be, in this picture they give you, A would be the distance from the surface of the Earth up to the satellite, right? You're not going to measure from the center of the Earth an altitude, right? And then the beam coverage provided by the satellite is shown in the figure. So, the closer the satellite is to Earth, the less spread out the beam will be and the less surface area it'll cover. Now, we've drawn the Earth as a two-dimensional picture, so we're thinking of the surface area not as an area but as an arc length, right? So S is this arc length from M to N, I believe. So the beam coverage provided by the satellite is shown in the figure. Part A, find the distance S, which is the arc length from M to N, as a function of the altitude A of the satellite. Assume the radius of the Earth is 3,960 miles. So we could actually label that. That would be this distance here. 3960. Whoops. Okay. It's important to understand, anytime you're solving a problem in life or in math, it's important to understand the problem before you start trying to solve it, right? How are you supposed to solve a problem if you don't really understand? But it happens in math all the time. Students will start writing down equations. They don't really know what they mean. So you really got to understand the problem. Symbolically, what we're saying is, in part A at least, we want that distance S as a function of the altitude A. So there's symbolism for that, right? S equals, what's the symbolism I've been using when you say y equals a function of x or S equals a function of A? What's the symbolism? S equals F of A. And just by writing that kind of generic function notation down, it tells you what you need, right? It tells you want that arc length S as a formula in terms of A, the altitude, right? So I think that's, being able to translate from words to symbols hugely important in just beginning to set up the problem in the problem-solving process, the first step. Does everybody understand what that means and what it is we're looking for then? Okay, now let's write down some things we know. First of all, we know an arc length formula, right? So I'm going to have to adjust it for this problem, but work with me here. Okay, let's say we just have a generic circle here, and we've got a piece of pi, pi, and then the arc length is this crust of the pi, right? It's not really. Well, in pi, I suppose it could be look like that, but in a circle, it's really a smooth piece of arc, right? And we often call that S. Of course, we call that the radius, and we call the point of the pi that corresponds to this angle theta. And what would the arc length of S be then in terms of r and theta? S would equal r times theta. There you go. So this formula is going to come in handy. Now, the thing is, it's going to be easier to think in terms of 1/2 S here in the picture we're giving. So why is that? Well, because if you look at what they've drawn, they've actually drawn something for you that can be very helpful. They've drawn here the beam coverage is S, the arc length from M to N. But they've pointed out that the beam, the widest part of the beam, if you think of that as a straight line, it's going to be tangent to the Earth. Where it hits the Earth, that straight line segment will be tangent to the Earth, and it'll actually form, this is a result from geometry, it'll actually form this right angle here with a radius of the Earth. So a line that's tangent, only touches a circle at one point, will be perpendicular to a radius of a circle. And they point that out here, and they point out then that if you think in terms of perhaps that right triangle highlighted in yellow there, that could be very helpful. But of course, then the arc length that we want to talk about is actually one half of what they're calling S, isn't it? So that's important to realize. So this arc length here then, that I'm trying to show you in green, is 1/2 S. And that's the one we're going to want to work with here. So we'll adjust our arc length formula from S equals R times theta to, well, it's still an arc length. 1/2 S equals R. 1/2 S is still an arc length. So 1/2 S will still be R times the corresponding theta. Does that make sense to you? Okay. So we're going to adjust the formula here and say 1/2 S, the S we're talking about right here, not the S we're talking about right here. This was generic, right? That was the generic formula. Just a reminder of what it is. So we know that 1/2 S, can you fill in, okay, R times theta, but what's R? What's the radius of the Earth in this case? 3960. That's in miles, but you don't need to put miles down until the end. 3960, and then what's theta? Well, I suppose we don't know, do we? And won't theta depend on the altitude that the satellite's at? So we're not supposed to know theta, because we're coming up with a formula in terms of A, and theta will change just like A does. So that's 3960 times theta. Any questions?
How do we know
Well, at this point, I'm not going to prove it, but certainly it's reasonable from the fact from geometry that if you take the widest part of the beam, I don't want to do that. Let's do that. Right. So the parts of the beam where this is a radio beam, radio signal. The widest part of the beam, the claim is that will be tangent to the Earth, if you think in terms of a radial or a straight line emanating from the satellite to the Earth. The widest part of that we're interested in, it might go wider, but the widest part that we're interested in that touches the Earth is going to be tangent right here at M, or for this part of the beam, or tangent here at N, right? So we're thinking then when we drop this altitude, it's going to split the total angle here in half, which would split the arc length in half also. So this arc length is in green is 1/2 S. I haven't proved that to you, but I'm telling you, you can assume that that's true. Okay, and it is, and you can prove it using geometry, but that's not really what we're interested in here. We're going to assume those facts from geometry. Okay, so 1/2 S is 3960 times theta, right? But what's the problem is, well, okay, I could multiply both sides by 2 and have S in terms of theta, right? But that's not what we're asked to find. We're asked to find S in terms of A. So looking at the right triangle in yellow, is there another relationship that connects theta and the altitude A, perhaps? So in that right triangle, maybe if I write it down kind of separately. This point, just for reference, this point's M. Can you tell me what this hypotenuse would be, looking back at the picture with the Earth? In terms of A, what would the length of the hypotenuse be? Well, it would be the altitude, A, right, plus the radius of the Earth, wouldn't it? Yeah. So A plus 3960. Does everybody see that? Do we know any other side? Yeah, we know that this angle's theta, which makes this side the adjacent side, and that's the radius of the Earth, right? From here to here. Does everybody see the triangle now that I've separated it from this? This picture started to get a little messy. Does everybody see? Okay. Now look, within this triangle, there's an A and there's a theta, and it's a right triangle. I think we know how to connect the dots here as far as getting a formula with both theta and a in it. So we've got theta, somebody already pointed out it's an adjacent side, and this side's the hypotenuse. What's the relationship there then? Let's see, adjacent and hypotenuse. That's an A and an H must be cosine, yeah. So you could say the cosine of theta is what? Adjacent, 3960 over hypotenuse, A plus 3960. Okay, my claim is you've got all the pieces of the puzzle now. So if you can just write theta in terms of A, so in other words, get a formula for theta in terms of A, couldn't you plug it in here? Multiply by 2, and then you've got S in terms of A. Is there a way to use this to get theta in terms of A? In other words, is there a way, essentially what I'm asking you to do is solve this for theta, right? Because that will get theta in terms of A. What could you do to solve this for theta? Oh, but that's the point. How do I get rid of the cosine in front of the angle? Take the inverse cosine of both sides. Does that make sense? So the next step would be to solve this for theta, and that's basically just taking the cosine inverse of both sides. You'll get theta on one side, cosine inverse of 3960 divided by A plus 3960 on the other side. Then plug and chug. Don't forget to multiply by 2 to isolate S.